Okay, thank you. And thank you for the invitation. It's very nice to be here. So I'm going to be talking about cluster algebras and mostly tree amplitudes. So there's already been a series of lectures in this program by James Drummond on cluster algebras, and many other talks that you've already seen have touched on cluster algebras. So I'm actually not going to spend a single minute reviewing the definition of cluster algebras. Instead, I want to start with a very brief introduction to some of the various places where cluster algebras have made an appearance in amplitudes or in things related to amplitudes. So very broadly speaking, we see connections between cluster algebras and tree-level amplitudes or integrands for loop amplitudes. This goes back to probably as far as the work of Arkani Hamed et al. In 2012, and of course many other people. And you've already seen talks related to this in the guise of the amplituhedron. So for example, the lectures by Melissa Sherman Bennett earlier in the program. Then we also see connections between cluster algebras and I'll say integrated loop amplitudes. These are polylogarithmic functions, typically in the simplest cases. And this connection was first observed around 2013 in our paper with Anastasia and Sasha Goncharov and Christian Vergu and John Golden, and many subsequent papers. You heard about it to some extent last week in Omer's talk, and there will be another talk later this week by Yorgos Papathanasiou, and many other talks will touch on various aspects of this correspondence. And then very recently, and when I say very recently, I mean, within a couple of months or even weeks prior to this conference, we've learned about connections between cluster algebras and cosmological correlators. So this was first realized in some papers by Livia Tomic and their collaborators Capuano, Palacio, and in a paper last week also with Yaoqi Zhang. And simultaneously with their first paper was a paper by Mazlumi and Zhu. And also we had a paper on it with Anastasia, Shruti Paranjapi, and He-Cheng Wen. So this is all relatively new. And you've heard this connection in Tomic and Livia's talk last week. This is relatively new, but I want to emphasize some of the similarities and distinctions between the different places that cluster algebras have appeared in physics. So a cluster, someone who spends their life professionally studying cluster algebras might think that, might see a universe broader than what we have need for, or what we've realized that we have need for in physics. So let me say the two most basic aspects of cluster algebras that we make direct use of in physics are just lists of cluster variables and compatibility conditions. So Omer ascribed to me last week a quote where I said that some of this was based on astrology, where we just look at the results of different difficult calculations. We observe that we get lists of things coming out of those calculations, lists of cluster variables in many cases, and that we observe certain patterns. We observe that certain of these variables are compatible with others in certain senses. And then we turn to our mathematician friends, and they have a machinery called cluster algebras that generates lists of variables, and they have a machinery that defines a notion of compatibility between various variables. And we observe that in many cases in physics, the lists of variables and the compatibility conditions that we get agree precisely with what the mathematicians tell us. So again, of course, to a pure cluster algebraic theorist, there's much deeper structure in cluster algebras that they might be interested in, but these are sort of the coarsest zeroth order things that we see in physics. And these are common to all of the appearances that we see. However, it's also clear that, and this is kind of a little bit different, also clear that the true story goes far beyond cluster algebras. And what I mean by that is that we see the emergence of cluster algebras according to the standard definition only in the simplest cases or in certain limiting cases. But the physics gets much more complicated as we look at more general cases. And that suggests that physics is trying to suggest possible definitions of structures that generalize cluster algebras in various ways. So let me give some examples of this, kind of going in reverse order here. On the cosmological correlator side, we heard in Tomek's talk last week that the path graph is associated with A-type cluster algebras. And in our paper last week, we studied the polygonal graph, the one-loop polygon, and we showed that it corresponded to B-type cluster algebras. However, it's pretty clear that if you took a general graph, you would encounter a structure that has these two properties. It has lists of symbol letters, which are completely explicitly known for any graph. And it sort of manifestly, I'm talking now specifically about the cosmological correlators in de Sitter space. They pretty manifestly satisfy a list of compatibility conditions, but they won't correspond to the cluster variables and compatibility conditions of any cluster algebra, maybe to some generalization thereof. For example, there was some discussion of connecting to Thomas Lamb's 2012 paper on LP algebras. So this is a venue where I think you're going to see these kinds of things for any kind of graph. And it's, despite the fact that this is the newest of the three, I think it's fair to say that this is the tamest and best well understood. You know, there's still several more papers to be written. I hope to write a few more myself with excellent collaborators, but you can kind of see where it's all going. In contrast, the cluster algebra story here for the integrated amplitudes is really much more mysterious and murky, because here we typically encounter in the simplest instances the Grassmannian cluster algebra 4, n, which becomes infinite starting at n equals 8. And there's a whole phenomenology or astrology about trying to explain some of the symbol letters that we see starting at 8-point amplitudes that are not cluster variables, but are algebraic functions of cluster variables. And that's a very interesting problem. There's many different approaches that are all extremely interesting. But the situation becomes even more complicated because we know that in general, amplitudes do not evaluate to multiple polylogarithm functions. You get elliptic or even much more complicated classes of functions. So it's not even clear how to ask questions about the connections between more complicated functions of those types and cluster algebras. So whereas this is kind of under reasonably good control, if you look at general integrated amplitudes, this is still quite wild territory. So in contrast, or that's kind of what motivates me to spend the rest of my talk talking about issue number 1 here, where there's a rich structure, but it seems not insurmountable. Okay, So I'll talk about one in the context of tree-level, color-ordered gluon amplitudes. Okay, so that ends my introduction, but again, just to summarize my introduction, I'll explain how the study of tree-level color-ordered gluon amplitudes suggests some natural ways of thinking about structures that generalize cluster algebras in order to explain the phenomena that we see in these amplitudes. Okay, so then I have two separate parts of the talk. The first part will be about momentum twistors, Yangian invariants, and GR4N. Okay, so the amplitudes that I'll be describing, these tree-level gluon amplitudes, are labeled by two integers. First, the number of particles, I'll call n, and then what we call the helicity degree. And when you work in what we call the momentum twistor variables, which is a certain way of parameterizing the energies and the momenta of the particles involved in the scattering, the amplitude, and I'll use this curly a, n comma k, is a certain rational function of Plücker variables on GR4 comma n. And we think of Z as a 4 by n matrix representing, it's a matrix representing a point in that Grassmannian, and it encodes the information of the scattering particles. If I continue writing so large, I'm going to spend most of my time erasing, so I'm going to try to compactify my handwriting a bit. Okay, ANK is often computed in practice by what we call the BCFW recursion, which expresses it. Let me pick on one board. Okay. Which expresses it non-uniquely. There are many different ways to run the BCFW recursion. You have choices at each step of the recursion. But no matter how you choose to run the recursion, you always get the same number of terms. And the number of terms is given by the Majorana number. Given by that formula. And so you can calculate this amplitude using the BCFW recursion. You get a sum of that many terms, and each term is individually a rational function of the Plücker variables. Now let me show you an example. One of the 6 terms for n equals 7, k equals 2 is, there's some numerator that I don't care about for the moment, and you'll see why, divided by 1, 2, 3, 4, 1, 2, 4, 5, 1, 3, 4, 5, 1, 4, 5, 6, 1, 4, 5, 7, 1, 5, 6, 7, 2, 3, 4, 5, 4, 5, 6, 7. Okay. I'm not done with the denominator. Then you get this thing that's quadratic in the Hooker variables. Okay. All right, so that's an example of one of the terms you get when you run BCFW recursion. And the point is that in 2018, Drummond, Foster, and Omer, sitting there in the back, just observed that that is a product of mutually compatible cluster variables on GR4, 7. So the denominator is a product of mutually compatible. That means there exists at least one cluster. In this particular example, I don't remember if it's one cluster or many clusters, but there exists at least one cluster that contains all of these cluster variables. Well, I'm sorry, I should say, first of all, the observation is that all of these are cluster variables. That already is a somewhat non-trivial statement. Then even beyond that, there's the statement that not only are they all cluster variables, but there exists a cluster containing all of them. So the denominator is a product of mutually compatible cluster variables on GR4, 7, and this property is what we call cluster adjacency at tree level. We also use the word cluster adjacency. In fact, adjacency has more of a meaning when you talk about loop level amplitudes and you talk about who's allowed to appear next to whom in a symbol. But anyway, this is what Drummond, Foster, and Gerdegon noticed, and it seems to be true in general. In fact, we can now consider it essentially proven thanks to our mathematician friends, as we heard in the lectures by Melissa Sherman Bennett. So let me switch now to the math. Because in physics, we often like to think analytically in terms of formulas. Okay, so we look at a formula like that. But many mathematicians, especially those who have a more combinatorial or come from combinatorics or from algebraic combinatorics, like to think more geometrically. So let me now briefly rephrase that statement in the manner that you've heard it, I'm sure, from Melissa's talks. So Chaim Evan Zohar, who also spoke at this program, Tzvika Lakrek, Matteo Parisi, Matteo is there, hi Matteo, Melissa, Rand Tessler, and Lauren Williams define a tile of the NKM amplituhedron. I'll use a different letter now. I'll use capital A rather than curly script A as follows. So first, you fix a positive n by k plus m matrix Z. Strictly speaking, I should use a different. I should use a different Z. This Z is very closely related to that Z, but not quite the same thing. Fix a positive n by k plus m matrix Z and define the map called the amplituhedron map, which maps the Grassmannian k comma n to the Grassmannian k comma k plus m by essentially matrix multiplication. So if you have a matrix C that represents an element of this Grassmannian, and you multiply it on the right by this n by k plus m matrix Z, then as long as this is a totally positive, a positive matrix, meaning that all the maximal minors are positive, then you'll get an element in this Grassmannian. Okay, I'm still not finished writing my definition. The next step is to let S be a cell of the totally non-negative Grassmannian k comma n, a la Postnikov, who showed that the totally non-negative Grassmannian has a cell decomposition. And then, to finish the definition, then Z tilde of S is a tile if, number one, Z tilde is injective on S. Now, usually it's not, because you're mapping here from a space to a much lower dimensional space. Remember that, I should say this, m equals 4 in physics. So what we're doing is we're kind of generalizing the notion. Here in physics, we're always interested in kinematics that's encoded in 4 by n dimensional matrix. Here on the math side, we allow ourselves the freedom to generalize that 4 to another integer. Anyway, so the point is that k plus m is always less than or equal to n. And typically, it's less than n. So you're mapping from a space to a lower dimensional space in general. And so it's very rare, it's typically not the case that this will be injective. Okay, so Z tilde of S is a tile if Z tilde is injective on S, and if the image is full dimensional. That means the dimension is mk. Okay, we want the map to be injective and saturating the full dimension of the target space. Okay, that concludes the definition of the tile. And now, how am I connecting it to that statement there? The idea is that finding tilings of the amplituhedron is the same problem, essentially, as computing the amplitude. And here I'm going to be very schematic, allowing myself to refer to other people's talks. To find a tiling of the amplituhedron means to find a collection of disjoint tiles, by this definition, that fully cover the amplituhedron. Each one of these, being a cell of the totally non-negative Grassmannian, is a positive geometry. It has a unique canonical form, a form with logarithmic singularities only on the boundary. You can take the image of that form if you push it through this Z tilde map, and that will give you some form in this space. Then you add up all the individual forms from your tile, and what you get is a rational function that can be interpreted as the amplitude. So adding up all the forms, I'm skipping a few details, but I'm giving the general idea. Adding up all the forms gives there's an overall piece that has all the form weight, like the dz wedge dz's, and the coefficient of that, because you're getting something full dimensional. So you have like an overall volume form times a rational function that computes this amplitude. Okay. So in this language, the individual pieces referred to there, the individual BCFW terms, correspond to these individual tiles. And the statement of cluster adjacency that I gave there is the statement that if you look at what is it that's carving out these individual tiles, the statement is that every tile is cut out by the vanishing of a set of compatible cluster variables. Let me emphasize that. Suppose this here is the tile. Suppose I'm doing that example, n equals 7, k equals 2. Then there would be 6 tiles, and suppose that red one is the one that I've written there. Then you can describe, you can give a set of inequalities that carve out that tile from the ambient space by saying that all of those factors in the denominator have to be positive. That gives you a set of inequalities that carves out this little tile. And so in the language of these mathematicians, the statement of cluster adjacency that we observe phenomenologically in physics is the statement that every tile is carved out by a collection of mutually compatible cluster variables. And that was proven by these authors in 2013, 23. So in this language, cluster adjacency has been proven for m equals 4. I should say that we had a 2019 paper with Tomek and Matteo and Anastasia that proved this, at least from the physics point of view, for m equals 2. I'll put m equals 2, 2019. Okay. Are there any questions at this point? All right, let's try this. Okay. I'll continue talking while I do this. All right. Now, oops, that's maybe a little bit too much water. Now, when I say that they prove this for a specific class of tiles that we call BCFW tiles. So a BCFW tile is one that appears when you run the BCFW recursion. So in other words, in order to phrase it differently, the BCFW recursion can be used to give you a list of tiles that will tile the amplituhedron. So, yes. So, but let me draw a Venn diagram and yeah. There are many different ways of running the BCFW recursion, and collectively, I'm referring to any tile that could ever possibly appear and running it any way as a BCFW tile. But certainly, it is true that there do exist cells of the totally non-negative Grassmannian that you will never encounter when doing BCFW recursion. So there are more general tiles than BCFW tiles. And in a 2019 paper with Jorge Mago and Anders Schreiber and Volovich, we conjectured and checked in several, numerical experimentation. We checked that for all tiles up to a certain number of n, I don't remember the details, cluster adjacency continues to hold. Okay, so this remains an outstanding mathematical conjecture. But the point I want to emphasize in my talk today is that in physics, there's an even larger class of objects that we study called Yangian invariants. So again, cluster adjacency has been proven mathematically for these tiles. It seems likely to be, let me write it here. Adjacency proven. Matteo and his collaborators in ongoing work have done a lot of work starting to map out this space, and they have many interesting results about it. I'll go out on a limb. It's likely going to be true, right? You have no reason to doubt that it will be true. But, okay, the point I want to emphasize in my talk today is here in this broader class of objects that we encounter in physics, we even have to refine the definition. We have to refine the definition before we can even make a statement about these more general objects. So this ties back to the theme of my talk being physics stimulating some possible ways of motivating generalized cluster algebras. So let me give an example. N equals 8, M equals 4, K equals 2 is the first example of a cell on which the Z tilde map is not injective, but 2 to 1. So it satisfies this criteria, right? So in physics, we can relax a lot of the assumptions, even more than are apparent here. But in my talk today, I'm going to keep assumption number 2. The image is still full dimensional, but I'm going to relax this assumption. Z tilde is no longer injective. Instead, it's 2 to 1. And we know from Postnikov's work that there's a bijection between cells of the totally non-negative Grassmannian and equivalence classes of certain Playbit graphs. And if you're an expert in that language, or at least familiar with it, I'll draw you the Playbit graph that corresponds to the cell I'm talking about. The image of this cell under Z tilde is carved out by quantities that are not cluster variables of GR48. I'm going to erase again and then remind myself to stop writing so large. I'm sorry? I believe, okay, Matteo, correct me if I'm wrong, but oh my gosh, I can't even read it in my own notes. Is that right? Yeah, the colored, so I have 2 black and 4 white, right? Okay. 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 I'm not going to give a full list, but if we define 2 quantities, 1, 2, 5, 6, 3, 4, 7, 8, 1, 2, 7, 8, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. This thing is not a cluster variable of GR48. This is also not a cluster variable of GR48. That combination is certainly not a cluster variable of GR48. Then, okay, those were just intermediate definitions. The tile is cut out by things like, there's a long list of them, but I'll just give a few. Delta greater than 0, A minus root delta greater than 0, and similar. So this is not a cluster variable of GR48. These things with the square roots most definitely are not cluster variables, because in cluster algebras you don't encounter square roots, although there are various natural generalizations, in particular a nice one by Omer and his collaborators on how to naturally associate square roots to cluster algebras. One important clue is that is positivity. So it's not obvious, but inside the positive Grassmannian 4,8, you can check it's true that A is greater than 2 root B is greater than 0. And this 2 cannot be reduced. So this quantity, A squared minus 4B, is strictly positive in the interior of the positive Grassmannian, and that would not be true if you substituted 4 with any number smaller than 4. So here you get, via this construction, certain quantities. So here's the point, and I'm ready to actually stop this portion of my talk. Obviously, this is a tip of an iceberg. There's an infinite class of cells of bigger and bigger Grassmannians where you get phenomena like this. The amplituhedron map can be not just 2 to 1, but arbitrary to 1. So you can get algebraic quantities of, in principle, arbitrarily high degree. And conjecturally, they will always have this positivity property that every tile, even though it's not cut out by cluster variables, is cut out by some quantity that is positive in the positive domain. And if you took seriously this notion of cluster algebras, you would want to call these compatible generalized cluster variables. Right? If you take seriously the idea that in the cases where we do have a direct connection to cluster algebras, these tiles or these denominator factors are mutually compatible cluster variables, and now you say, hey, I want to generalize that structure to these more general cases. Well, physics gives you these lists of things that it suggests you consider compatible generalized cluster variables. Yes, Omer. Please. Yeah. All right, so that concludes part 2 of my talk. And I want to switch now to part 3, where I talk about a different set of kinematic variables called spinor helicity variables. And I'm going to introduce a word called split helicity. You'll see why in a moment. And the partial flag variety 2 comma n minus 2 comma n. Okay, there's another description of the kinematics of n massless particle scattering called the spinor helicity variables. And here we have lambda and lambda tilde that are two real 2 by n matrices such that lambda lambda tilde transpose, that's a 2 by 2 matrix, and it has to be identically 0. That's what we call momentum conservation. And we define these brackets to be the Plücker variables of these matrices. So now helicity amplitudes are essentially the same thing as what I was describing previously, except for one small difference, which is that when we talk about a helicity amplitude, we're only looking in the sense that I didn't previously define, at a certain component of what we normally think of as a super amplitude. Practically, what that means is helicity amplitudes depend on a choice of helicity plus or minus 1 for each particle. So we have to write a notation. Notationally, we just put a subscript above each particle label. So to give you some idea, the 3 particle amplitudes, which are kind of special cases. When I started my talk, I told you that n will always be at least 4, but the 3 particle amplitudes exist as special cases. And I'm just writing these down to give you a flavor. Again, you get rational functions of the various spinor helicity brackets. And as before, you can compute more general amplitudes via BCFW recursion. Indeed, you can sort of write a closed form for the solution of that recursion. There was a nice paper of James Drummond and Johannes Henn that did this a while ago. But the solution to BCFW recursion takes a very simple form. And this will be the focus of the rest of my talk, for what we call split helicity amplitudes. Split helicity amplitude, those are ones where all of the negative helicities are cyclically adjacent, and all of the positive helicities are cyclically adjacent. So for the rest of my talk, I'm going to consider that specific split helicity amplitude. Okay, while I'm erasing, I can tell you some of our motivation, which was, it's recently been discovered, as you heard last week from Omer, and as I anticipate you'll hear from Yorgos later this week, that the spinor helicity amplitudes, first of all, there is a natural embedding of the spinor helicity variables into a partial flag variety, f2 comma n minus 2 comma n. Number two, that there's a natural cluster structure on that partial flag variety due to Bossinger and Lee here in the audience. And third, as you heard about in Omer's talk, and we'll hear from Yorgos, that cluster structure has been useful in explaining some of the patterns of symbol alphabets that we see in amplitudes beyond n equals 4 Yang-Mills theory, in particular to QCD. So the motivation for our current work which was written up in a paper last fall with Anastasia and Andrzej Pokraka, who's there in the audience, and Yicheng Wen, is that the motivation was to see if it's true that there's some analogous structure in the BCFW term. Is there a notion of cluster adjacency for BCFW terms in spinor helicity variables that's analogous to the statement of cluster adjacency for GR4, comma n for the in the momentum twistor variables? Okay, so to answer that question, I can write an explicit formula for that amplitude as a sum from k equals 0 to the min of q minus 3 n minus q minus 1 of all k zigzags. What is a k zigzag? K zigzag is a choice of a subset A of the indices 2 through q minus 2 of cardinality k, and a subset B of q plus 1 through n minus 1 of cardinality k plus 1. Okay. So the total number of terms will be the sum from k equals 0 to the min of q minus 3 n minus q minus 1 of q minus 3 choose k times n minus q minus 1 choose k plus 1, which is n minus 4 choose q minus 2. Okay. Now, we call it a k zigzag because we choose, and I'm going to try to use the whole board for this. We use a graphical notation to introduce the terms, or to keep track of the terms So let me draw an example. Okay. One of the 525 two zigzags that contributes to n equals 17, q equals 9 is, I'm going to describe it in words now. A k zigzag is a you first of all, you draw a line here at the top, and you put all your negative helicity gluons in order. Then you draw a line at the bottom, and you put all your positive helicity gluons in order, continuing the cyclic order. Then a k zigzag is a non-self-intersecting path that bounces back and forth between the top and the bottom. And the rule is you have to start here, you have to end here, and you have to bounce back and forth, always landing at the intervals between points. So let me show you one term that contributes to this amplitude. Maybe we should have shifted the definition of k by 1 to call this a 3 zigzag because it bounces 3 times. Okay, yeah, sorry about that. According to the definition there, this is a 2 zigzag. Okay, this is one of the terms that contributes to this amplitude. Now, I need... Okay, so there's a graphical way to encode contributions to this split helicity amplitude and spinor helicity variables, but I need to give you a flavor of what the corresponding formula looks like. Because remember, what I'm trying to do is make some kind of statement about cluster adjacency. Yes. Oh no. Oh no. Did I see? I changed the numbers at the last moment of my talk. And I knew that was dangerous and precarious with you sitting in the front row because, okay. I changed my example in the last minute. So. Thank you. Thank you. Yes. I should have indicated that. A and B are telling you where the, so I'm going to choose, this will be A1. This will be A2. So there, it's telling you basically the left of all of the places where you hit the top row. And B, analogously, is the choice to the right of wherever you hit the bottom row. So here I made a choice 3 B's and 2 A's. You have to start here and end there, but then you have a choice where you hit in the meanwhile, and down here you have a similar choice. So thank you, that's my definition of the A's and the B's. Right, that's the total number of all zigzags, but what's the number specifically of 2 zigzags? Okay, the denominator of the associated term, it's quite a mess. It's first of all a cyclic product of all these brackets up to n comma 1. Then it's a cyclic product of these brackets all the way up to q minus 2, q minus 1. Then it's a cyclic product. So this, by the way, I didn't give the citation for it yet. This was in a 2005 paper by myself with Anastasia, Ruth Brito, and Bofang and Radu Royban. There's a notation here I haven't defined, but we'll do so in a second. It's kind of a mess, certainly not the kind of thing a civilized person does in the last 5 minutes of their talk, but it's meant to indicate that there is actually, hopefully, some content here. This thing is defined as the sum over all A from I to J of Ka Al. Okay, so that's a review of the 2005 result. Now, I've already given the motivation, so I'm actually slightly ahead of time. There's an embedding of the spinor helicity variables into the partial flag variety. How you do that is if you take an n minus 2 by n matrix, let's call this M. So the top 2 rows, that's a representative of the 2-dimensional component. So here I want to discuss the partial flag variety 2 comma n minus 2 n. That means 2-dimensional subspaces of an n minus 2 dimensional subspaces of an n-dimensional space. So I can parameterize an element of that partial flag variety by looking at a matrix of this form, where n corresponds to the top two rows. Then the correspondence between the spinor helicity variables and the partial flag variety is that ij gets identified with the determinant of ni and j, and the bracket ij gets identified with -1 to the 1 plus I plus j times the determinant of the product of all m's, except you cross out I and j. Okay, that gives the embedding of the spinor helicity variables into the partial flag variety. Okay, so as I already reviewed, recent work starting with Bossinger, Drummond, and Glue, and then later also with them and Omer and Rowan White, and our paper with Andrzej Pokraka and Hicheng Wen last year, and you'll hear more about this in Papathanassiou's talk tomorrow or later this week, indicates that the cluster structure in the partial flag variety described by Bossinger and Lee has been useful in explaining some features of QCD symbol alphabets. So we wanted to see if there's a cluster adjacency story at tree level as well. Now, one of the unusual features of this correspondence is that and Omer mentioned this in his talk, this is very unusual for people coming from the Grassmannian point of view. You have to take the union over all possible ways, over all permutations of the embedding of the spinor helicity variables. In order to get the full symbol alphabet, you have to allow yourself arbitrary permutations of the kinematic variables. Let me make myself one more board. I am almost done, surprisingly, but not quite. I may take you up on your offer, Oliver, of going a minute or two over. So, unusual feature must take union over permutations of particle labels. So the question we asked in our paper, for a given zigzag, i.e. BCFW term. So in this context, BCFW terms are labeled by zigzag diagrams. Do there exist any permutations such that all factors in the denominator are mutually compatible cluster variables of this partial flag variety, 2n minus 2n. And we answered this in the affirmative, although I should say that our paper is not even a proof by physics standards. We check in a number of, we checked in as far as we could go on the computer. So this remains a conjecture that maybe might be interesting for some of our mathematician friends to look at. But we found the answer is yes, and let me explain how to find the correct permutations. Here's the list of permutations that work. Okay, so in my last 2 minutes, I'll describe how to read off from the zigzag diagram a list of permutations that renders that whole denominator there a product of mutually compatible cluster variables. Now, first of all, I need an aside to define something, and this was the contribution of ChatGPT to our paper. Because for me, so far, ChatGPT has only served as a glorified search engine. We encountered some certain classes of permutations and wondered if they had been encountered in the math literature before. And ChatGPT gave us a 2010 reference by Adden and Reuchmann, where these are called arc permutations. So an arc permutation is a permutation, it's an element of Sn, such that for all k in 1 through n, the set pi 1 through pi k is an interval. That means they have to be adjacent. So example 2, 3, 1, 6, 4, 5 is arc, but 2, 6, 1, 3, 4, 5 is not. Basically, if you start with 2, then the next element has to be somebody who's a neighbor of 2. So you either go to a neighbor or you arc all the way around. 3, so 3 is a neighbor. Now you have 2, 3. You need a neighbor. You could put here a 1 or a 4. You put a 1. Here you could have put a 6 or a 4. Okay, this is not an arc permutation because if you start with 2, then you jump to 6. That's not allowed. I'm actually curious if any mathematicians have heard this phrase or have seen this concept by a different name. Okay, so we'll use what we call rooted arc permutations, where a specified index with a star must appear first or last in the permutation. Okay, so I'm going to use a notation. I'll put a little star above one of my indices. Okay, now since I'm out of time, let me explain how it works in this example. We want to read off a set of permutations from this diagram. The first step, well, there's a minor bookkeeping step that I'm skipping that doesn't apply to this diagram. It applies to certain degenerate diagrams. First, we give the arc an orientation, the zigzag an orientation, starting from the left here. Then, we're going to consider the regions here. So these indices all belong to the left region. Sorry, I left one off. These 4 indices belong to the left region. These 3 indices belong to the right region. And then I have this region, this region, that's by itself, and that's by itself. Now, here's what I'm going to do. Do I have another color? Sure. The orientation of this path tells me to star 15, and the orientation of this path tells me to star 11. The general rules are given in our paper. Here I have 4 indices. So I'm going to I want to write down a permutation. And I'm going to write down the first 4 indices, 1, 2, 3, 4, belong to this region here. except 2 will be starred because 2, like if I were to read this in literal cyclic order, it would be 1, 2, 3, 4. 2 would be starred. Then I allow myself arbitrary arc permutations of these 4 indices. Now I read through the diagram from left to right. I assign, for these interior regions, I assign 5, 6. This is the next region I reach. 7, 8. This is the next region I reach. 9, 10, 11, 12. This is the next region I reach. 13, 14. And here in the end, I have arc of 15, 16, 17 with a star on 17 because it's the last. Okay, so the statement is that if you consider an element of the permutation group on 17 letters given by any rooted arc permutation of these 4, followed by this particular pattern and ending with any arc permutation of those 3, then the numerical evidence suggests that formula satisfies cluster adjacency with respect to the partial flag variety. Okay, so that concludes this part of my talk, except to say that the natural setting for answering this question should be within the context of what we call the momentum amplituhedron, which was something that was introduced by Livia, Tomek, and Matteo, who are all here. We struggled a little bit with that because, well, we couldn't find a way of making an interesting statement that seemed to work. So we restrict our attention to the split helicity amplitudes, which have a much simpler structure. Okay, but this is just another example of a mysterious kind of connection between tree-level scattering amplitudes and cluster algebras. And just to bring it back to the beginning of my talk, is one of the many interesting connections that we see between cluster algebras and amplitudes more generally. So thank you for your attention. I look forward to a fantastic week with all of you.